I'm Dev. I'm a graduate student at UC Berkeley, and I'll be talking about clickjacking. This is joint work with folks at UC Berkeley, in particular my collaborators Warren, Shive, Reza, and Don. And so let's get started. Wikipedia defines clickjacking as this technique of tricking someone into clicking on something different from what that person had perceived and what he thought he was clicking on, he or she thought was clicking on. And so classically this has been achieved using the original clickjacking word, started off using transparent iframes and stuff like that. Today I'll be talking about some new clickjacking attacks that really get into this idea of an attack on human perception, that clickjacking is fundamentally about what the user perceives, and so what are the limitations of human perception that we can use to trick the user into clicking on something that the user did not want to click on. We'll follow up, I'll talk about 5 attacks, and I'll talk about an evaluation we did with on Mechanical Turk. So before I get into all the attacks, a short intro, very quick on what the attack setup is like. There's a sensitive button that wants to be framed, but does not want jacked or tricked clicks. So X-frame options is not really a solution because the sensitive button does want to be framed. Think of Facebook like buttons or the PayPal pay button. These are scenarios where you have a sensitive UI button, but it's not, X-frame options will just disallow the framing, which is not what they want. The attacker wants to trick the user into clicking that button. In our case, for this talk, I'll focus on a Facebook like button, but it can be anything. And the attacker can convince the user to play a game on a page. The particular attack scenario is that the attacker can completely frame the Facebook like button, but has no control over the Facebook like button's display. So for example, there is no transparency it can set on the Facebook like button. The Facebook like button has to be fully visible. The attacker cannot overlay on top of it, cannot draw things on top of the like button. But on the remaining page, the attacker has full control. So as an illustration, this is the attack scenario. There's an attacker page. The red area is something the attacker can draw completely on, but the like button is something the attacker does not control at all. He cannot overlay on it. He cannot change the transparency of the like button. That's completely off mounts. And so all the previous attacks that usually people talk about when they talk about clickjacking focused on like buttons being half visible or something else overlaying on top of it. That is not what we'll be talking about. And furthermore, to bypass proposed defenses like the W3C UI security specification coming up, not only do we require that the full like button should be fully visible during the attack, it should also be fully visible for a noticeable amount of time. So let's say 500 milliseconds at the minimum. So this is to bypass, this is to not allow attacks where you trick the user into quickly clicking through. We want the like button to be fully visible for some amount of time. This is the UI security specification at W3C, and so all our attacks attempt to bypass this proposed UI security specification. Does that make sense before we jump into the attacks, roughly? All right, cool. So the first attack I'll talk about is the destabilizing pointer perception attack. This is about confusing the user's idea of what the pointer is and where it's going. All the attacks today, I'll be using a lot of videos and demos of the attacks. Videos tend to go wrong, so hopefully Murphy's Law doesn't bite me, and I'll say a little prayer and see what happens now. All right, so the attack starts off like this. The attacker convinces the user to go to a page and click on start playing over here. For the rest of the talk, the yellow circle is the real hardware pointer. And remember, the attacker can draw anything anywhere what he wants except the like button. I'm going to slow things down to make it easier to understand. And the game starts off. The user is asked to click here, the here link at the left. And we want to trick the user into clicking on the like button. So simple stuff. The user is thinking he's clicking on here, and we want to trick the user into clicking on the like button. So the yellow stuff is the real hardware pointer, and the arrow is a fake thing drawn by the attacker. So things start going wrong when the user starts moving towards the top. The hardware pointer keeps moving towards the right, but the fake pointer starts moving towards the left. This really confuses the user. And this goes on for a while, and the attacker ends up confusing the user into clicking here. I'm just going to give an illustration. I'll get into more depth on what exactly is happening. But does that make sense? The red area is the fake pointer that we drew, and the black line is the real hardware pointer. So the user started moving towards the top, and we drew a fake pointer trying to trick the user into saying that this is the fake pointer. I'm going to run it again on full speed just to reiterate what's happening. All right, so it starts from the bottom left, starts moving towards the left, and the user is tricked into clicking. And so what exactly is happening here? This is the figure I was just showing. The red area is the fake thing that we are drawing, and the black line is the real hardware pointer. The player starts moving the mouse from the bottom left because that's where we kept the start the game button. Fake pointer starts moving slowly towards the left a little bit. This confuses the user. The user wants to keep moving up and right, but the fake pointer is moving towards the left. The user tries to move further towards the right to make sure that the fake pointer gets to the real position. This keeps going on, and they finally really close to the target, the user gets really annoyed what is happening and quickly moves makes a sudden movement towards the right. And when he makes the sudden movement towards the right, the black line, the real hardware pointer, ends up on the Facebook like button, and the user ends up clicking on the Facebook like button. Now, one problem here could be that once the real hardware pointer or real mouse pointer ends up on the like button, the real mouse pointer shows up. We can't control what shows up on the like on top of the like button. So attacker has no control over that area. So the key idea in making sure that the attack succeeds is to distract the player's attention with lots of moving images. And so that was all like a small, easy demo, but I'm going to show you the real attack and what it looks like. All right, so same thing. And lots of fake pointers start coming in. This really confuses the user. Now I've paused it for a moment here, but as you can see, there is a fake pointer underneath the like button. Note that I'm not allowing the fake pointer to overlay on top of the like button because that's our threat model, that we cannot draw on top of the Facebook like button. So things are lots of fake pointers around. All right, does that attack make sense? I'm going to just show it again once more. All right. So what are we doing here to confuse the user's idea of where the pointer is? We are using this trick called crowding. This is a well-studied phenomena in human perception. Any stimuli surrounding a target makes the target less visible because humans want to conserve their attention. Attention takes up a lot of our brain power, so they try to conserve the attention. So when you have lots of moving stimuli, those moving mouse pointers, humans are trained to start ignoring it very quickly as a source of unnecessary distractions. And so this is the effect we are using over here to make sure that the user or the player does not take a look at the like button area and get tricked into clicking. Another possibility that another thing that we could have tried would be a phenomenon called filtering. Suppose we had a moving background behind the like button or something flashy behind the like button. After a while, initially the brain will look at it. The brain will ask us, oh, that's some interesting stimuli, let's take a look at it. But after a while it will realize that it's not something useful and start ignoring it as a source of unnecessary distractions. And then we can do the attack in that area because we know that the human will not take a look. And so I'm talking about these two because in general, controlling the attention of the user is a very useful thing in all attacks that you can do when it comes to human perception and UI security. The second attack I'll talk about is attacking peripheral vision. The idea is that the quality of our vision system in our peripheral area is pretty terrible. So the game setup is like this. Simple stuff. The sensor button is at the bottom left, and the user has to click on the left mouse button if the L block comes down, and the right mouse button if the R block comes down. And the game continues like this. This is an easy to imagine game. It's not hard to make it. I'll have demos at the end of this talk. And so, L block comes down, the user has to click on the left mouse button. So what is happening in the user's brain when he's doing this game? Well, this is the setup. We have asked the user to leave the mouse at the bottom left of the screen, the sensor area, but we have asked the user to focus on the top right of the screen. And now I can quietly replace the left bottom area with the like button. That's what I've actually just done on this slide. I don't know how many of you just noticed, but at the left bottom, I have added a like button. And so now it's not hard to imagine what an attack would look like. Concretely, in terms of a timeline, we show the sensor button, the L block comes down, the user clicks the left click. And after that, we replace it with a like button, have a little pause. And after that, we have another L block again. And this tricks the user into clicking on the Facebook like button. This attack really shows the importance of attention. And also, the user will not notice this because the quality of our peripheral vision, which might take a look at this corner area, is not very good. So user will not notice this switch that we have made. All right. The third attack gets into something much a bit more interesting. We attack limitations of the human motor system, the motor system being the neural system that controls all our actions. The phenomena we use is motor adaptation, where we get trained to do the same tasks again and again very quickly. So again, the game setup. Simple game, an asteroid is moving around in a game area, and every time the user clicks on it, the asteroid explodes, mineral pops out. The user has to click on the mineral to gain points. This keeps going on and on for a while. So what's happening here? Well, this is the illustration of the same thing. Player is presented with an asteroid. When the player clicks on it, the asteroid explodes and a mineral pops out. The mineral is produced always at a constant distance from the asteroid. Now we get the user to do this game again and again and again. After a while, the user gets used. His motor system adapts to doing this click, move, click action again and again very quickly. The user's motor system adapts to do this in a single shot, in a single stroke. And after a while, to do the attack, once we know the user has been trained, well, it's really simple. We replace, instead of putting the mineral where we wanted, we put a like button. The key thing here is that once we have trained the user to do this click, move, click action, the user cannot cancel midway. Once he does the first click, he cannot cancel the second click. That's really, really hard for a normal human to do. And so even if the user sees the like button and wants to cancel, it's very hard for the user to cancel that action. And so I talked about earlier that we'll use other attention distracting effects like background motion. And so the video I showed you had like a black background, but that's not what we really do. We have lots of distracting backgrounds to make it even harder. So I'll give you a demo for this particular attack, but remember for all the following attacks, that's really what we do, lots of distractions in the background. So lots of stuff happening in the background. This makes sure that when we bring in the like button, the user does not notice the like button coming in, because of all the random things that are happening in the background, the user learns to ignore them. So when an actual like button comes in, the user does not see it. And this is what I'll do in the rest of the attacks. I won't talk about it, but the fourth attack we use is this fast motion mislocalization attack, which is based on our limitation of the limitation of humans to not be able to really figure out the exact location of a moving object. So again, the game setup. So again, asteroid, but this time it has an arrow moving around in circle, and then when the arrow stops, a mineral pops out in the direction of the arrow. So the user has to click on the mineral as soon at its final displacement, as far away as he can, and the user gets more points for that. Simple stuff. So again, an illustration, an arrow, moving arrow, player presented with it. When the mineral pops out, the user must click on it to get the points. Notice that the user actually ends up always clicking a little further away from the actual position of the mineral. The reason for this is this illusion called the flash lag illusion. This is a well-studied illusion in human perception where a moving object at a particular instant always looks a bit further than it actually is. Neuroscientists believe that the reason for this is that brains inherently have an idea of inertia, and they believe that a moving object can't suddenly just stop. So we tend to assume that it will be a little further away than it actually is. So we still award points every time the user clicks a little bit further. We keep doing this game till the user achieves that click a little bit further, and then we put a like button at that location. The user does not realize that he's clicking on the like button. He thinks he's clicking on the mineral, and so we end up tricking the user into clicking the like button. Again, note that the like button is fully visible for 500 milliseconds, actually more than 500 milliseconds, and so this bypasses this idea of the like button should be fully visible for some amount of time. We are still able to trick the user into clicking on the like button. All right, the final attack that I'll talk about is visual cues and click timing. Game setup again. So all of these attacks are just games that, and we're lazy coders, so we use the same stuff, same images again and again. So the game involves just an asteroid moving around in a game area, and when the asteroid turns red and the user clicks, the user gets 3 points. If the user clicks when the asteroid is gray, the user gets -1 points. And this keeps happening for a while. Slowly, the speed of the asteroid will increase. And so same illustration, negative points for clicking on the gray asteroid, positive points for clicking on the red asteroid. Now it's not hard to imagine the actual attack. Move asteroid under a like button and change it to red. Because our brain has been trained to click as soon as the asteroid turns red, we tend to end up clicking on the like button despite the asteroid being underneath a like button. Now, one problem here is that there is a like button. The user might not want to click, might see the like button and try to cancel his action. To understand what is happening here, we use this model of response inhibition called the race model. The idea is that the color change of the asteroid, the color of the asteroid changing to red, is a go signal for the user to do a click, right? As soon as the user has been trained, as soon as the asteroid turns red, do a click. But the presence of the like button is a stop signal. As soon as the like button sees, the user is surprised and the user wants to cancel the click. An attacker wants to increase the time between the go signal and the stop signal. One way to do that is add lots of distracting images so that the user does not notice the like button. And so by the time the stop signal is received, the stop signal being noticing the like button, the go signal has already achieved that click. Another thing that the attacker could do is decrease time between go signal and actual click. Train the user to click as soon as he sees the go signal, the color change. And so we maybe award more points if the user clicks closer to the color change than further away. And so these sort of tricks, these sort of game tricks can help us improve the accuracy of the attack. We haven't actually implemented any of these, but these are some thoughts on how to improve these attacks even more. So we evaluated this on around 250 mechanical Turk workers, all the 5 attacks, 50 workers for each attack, and some subjects exited before actually completing the whole exercise. So many times the number of subjects is less than 50, but the success rates are pretty high. The first one has almost 100% success rate, and I've shown it to a couple of my friends, and even after knowing about the attack, the first attack still succeeds. So I'll suggest you try it out at the end of this talk. More interestingly, attack 2 through 5 are all attacks that work fine on touch devices too. And so, this is not just about pointers and tricking the user's notion of where the mouse is. These things work even on touch devices. So as tablets and mobile phones get more popular, you have the shared user interface in any place, these attacks could be interesting. And finally, this is only a lower bound on the quality of the attacks. You can do much better. First of all, our attacks are really simple. We are not game designers, right? Like if you must have looked at the videos, they're pretty terrible. We're not game designers. We're not EA. If I was a game designer, I would not be a grad student at Berkeley. I'd be earning a lot more money at EA or Zynga. But you can improve the games a lot more, make them more immersive, dynamically adapt the attacks, adapt the games as the user plays them. For example, get a better model of pointer movement and click prediction to improve the success rates of these attacks. Right now, each attack targets a completely different limitation of human perception. One was motor adaptation, one was on visual cues and timing, and another was peripheral vision. But a combined attack that ties all these things together could be really powerful, and I'm pretty sure it could achieve a 100% success rate. And finally, all our attacks work with a very strong defense. We make the like button visible for 1 second at least, and often up to 3 seconds. So, this is not practical. If the UI security specification is adopted and deployed on the web, I don't imagine Facebook or PayPal agreeing to a level as high as 1 second for the amount of time the button should be visible. It's probably going to be closer to 250 milliseconds. So the success rates of these attacks on a real world deployment would probably be much higher. And finally, human perception is a lot more complicated. We did very simple stuff. We had a neuroscientist in our team, so he helped us out a lot. But human perception is a very vast and well-studied topic since 100 years maybe. And so many more attacks are possible. For example, a very famous experiment is this change blindness experiment, where you just fail to notice stuff happening in a scene that you're looking at. And so, the classic experiment is the invisible gorilla experiment, where humans are asked to take a look at people playing basketball or something like that, and they do not notice a gorilla coming into the screen and dancing. It sounds crazy, but it actually works pretty well. Check out that URL, invisiblegorilla.com. It has videos of this attack and see if the attack ends up tricking you. But if people don't notice a gorilla dancing on the screen, we can probably convince them to not notice the like button when it pops up on the screen. And so in conclusion, secure UI design till now has worked with this model of, if this sensitive button is fully visible for some amount of time, we are safe. That is not a good enough model, according to me. We need to really start taking human perception and limitations of human perception into account while designing secure user interfaces. And Possibly some changes are needed to the UI security specification, or maybe just the fact that the specification is not a panacea and it's not going to solve all our problems. But fundamentally, just designing a secure user interface mechanism is critical for security. Anytime we ask the user to provide us an answer to a question, someone could trick the user. So it's important to think about these secure user interfaces every time you have a shared, anytime you have an area shared between an attacker and a sensitive button or a sensitive decision. That's all for me. Thanks a lot for listening. Badge out before you leave so that you can give feedback. And my email, the first URL is a demo of all the attacks. My email is the second line, and my homepage is the third line. And thanks a lot for listening. Thank you. I think we have 5 more minutes if anyone has any questions. Yes?
Context you supplied for these examples is a gaming context. And I wonder what sort of thought you put into clickjacking from, say, an e-commerce perspective or other sort of higher stakes context.
So even in an e-commerce perspective, the sensitive button would be an e-commerce button, say a PayPal button. But to trick the user, we can still use a game, right? So yeah, we can. Yeah, I agree that it is possible to make a lot more. It would be much more high stakes and a lot more interesting in an e-commerce context. I didn't want to make that argument because in e-commerce, I have some friends in e-commerce and they have a lot of other fraud detection mechanisms. It's not just a click that is used to. But I think yeah, it will be just as possible to do these attacks in those contexts. Yeah. Yeah.
Do you guys have thoughts about how to make it actually more secure, like in addition to the requirement of?
So the question was, do I have any thoughts on how to make it actually secure, or in terms of defense, what can we do? I have thoughts, but no, it's a very hard problem. I think maybe machine vision, computer vision, because these are attacks on human perception. Maybe we can use machine perception, which is computer vision. But it's hard. Humans are not not algorithmic, so it's hard, and I am working on it. But yeah, very, very basic thoughts. Maybe we can discuss it offline, but it's not easy. Anyone else? All right, thanks for listening. And please talk to me offline if you have any other questions. Thanks a lot.